Greetings. In this one, I'm talking about this gas equation related to the ideal gas law, and what it does is it relates different quantities concerning a particular gas together. So namely, it considers pressure, which is P, volume of the gas, the amount of moles of the gas, then this constant connects it all together, and the temperature of the gas all together in one equation. And just to make it clear, the units I'm using here are the basic, simple SI units, probably the most simply choosable units for this scenario. So in pressure, I will put it in pascals, which is basically Newton per meter squared. Volume, I will put in meters cubed. And amount of moles, well, basically that's amount of moles. So amount of moles, R is 8.31. That is called the ideal gas constant that I'm using here. And temperature, it is in kelvins. Kelvins basically what it is. It's the amount in Celsius plus 273. It is one takes the temperature in Celsius. So let's say if the temperature is 20 Celsius, then that equals around 273 more, which is 293 Kelvin. Alright? 1 adds 273. 0 Kelvin is minus 273 Celsius. So, the example that I will be taking into account here is one in which I will use all these different parts of this equation in order to calculate the temperature based on the other quantities. And by the way, just to explain one thing that might not be clear yet is this N. What this N is, it's amount of moles of the gas. And basically gas, it's made up of molecules. So the amount of molecules is given in moles, and that means that each mole has a particular magnitude. And 1 mole is equal, it's also called Avogadro's constant, and it is equal to approximately 6.022 times 10 to the 23. So 1 mole means that I have this many molecules of the gas. If I have 2 moles, then I have 2 times this amount of molecules of the gas considered. So this N, if it's a small n like this, it means not straight away the amount of molecules enumerated as a number, but it means the amount which will further be multiplied by this Avogadro's constant. So if this is 2, that means that the amount of molecules is 2 times this entire number. So let's say that I have a gas and I have 2 moles of it. So 2 moles, that means that will basically behind all of it mean it is 2 times the Avogadro constant amount of molecules of the gas that I'm considering. Let's say the pressure is 300 pascals. Let's say the volume is let's say 20 meters cubed, and let's say that the R, by the way, that's a constant, is the ideal gas constant. It is 8.31. all right, and the units for it, well, I can add the units right here. It's newtons per meter squared, in other words pascals. But in the end, it all connects together when the correct units are used all together. Then I don't have to use them on the way. It actually takes up space to use them on the way. Newtons per meter squared, then V is basically in meters cubed, as I've already said. And this is amount of moles, this is the constant, and this is temperature. Of course, this is per mole times amount of kelvins. But it's not necessarily important to mention over what units this constant, the ideal gas constant, is. I'll just talk about 8.31 as the value of it. So right now, this equation relates all these quantities together, and what I want to figure out is the temperature. So I can divide both sides by NR, and I get PV over NR. So this way is how I can get the temperature. As I said, the temperature will be gotten in kelvins at the end. So what this gives is T equals PV. Well, P is the pressure in pascals, 300. Then V is 20 meters cubed. I'm just using the magnitudes without the units, just to make it simple, because I know at the end the temperature is given in kelvins, by the way. So I will put the K at the end of the fraction here. And then it gets divided by the amount of moles. Actually, I don't even have to use Avogadro's constant, because this way around is very useful. N is 2, I have 2 moles, so I don't have to write that huge number and work with it. And that's what helps me with that is basically this constant. This constant helps me to circumvent the usage of the Avogadro's constant. If it was not used, then a different constant would be used. If the exact amount of molecules was to be used, in most cases, bigger numbers would be used, and then a different constant would be used besides that. So instead of the R being 8.31, if here it wasn't the amount of moles, but it was the actual amount of molecules, then a different constant would be the R. This would be, by the way, capital N. In the case it was talking about straight away the amount of molecules and not just the amount of moles of the molecules. And the constant used here, the R, would be a different value. So I further plug in this. So N is 2 and R is 8.31. So basically I'm at the finish now. I can just complete this. This gives around 20 and 2 cancel at 10 on the top here. So it is approximately 3. It's actually, so far, using the numbers that I've given here, it is 3000 over 8.31 kelvins, which it will evaluate at something more than 200 kelvins. So you can use your calculator to evaluate this value, and then to convert it to Celsius, use the 273 unit difference that I mentioned earlier. But anyway, this is the result. This is the temperature in kelvins based on the quantities that I have mentioned previously, and we used this equation in order to arrive at the